Hello. Here we will use diagonalization of matrices to compute number of paths in the graph, say like that. So we have three vertices and we have three edges between them, and well, really more than three, because unoriented edge means that we have edge there and back. So let's just draw the adjacency matrix of that graph. What will be 3 by 3 matrix, and then matrix entry will be counting how many edges we have, and in between any two, the number of directed edges will be at most 1. So there will be no edges from the first, which is here, to itself. There will be 1 from the first to the second, and there will be none from the first to the third, which is here. Continuing, we will have one edge from second to first, just going in the opposite direction along this unoriented one. We'll have one edge from the second to itself. This loop is unoriented, but it counts just as one. And then one from the second to third. And then really, because we don't have any orientation on edges, it means that we have edge there and back, which in the matrix language means that the matrix is symmetric, so we can easily fill it out. So that's the adjacency matrix of the graph, and the task is to compute the number of paths between any two as long as it takes. And that is, of course, computed by matrix entries of the nth power. So if we're interested in path of length n, we need to see matrix entries of the nth power. And that's where diagonalization will be helpful. We will have compact formulas for those matrix entries. So let's start by finding the diagonalization, but finding first the eigenvalues. That is done through characteristic polynomial. These eigenvalues will be the roots of that polynomial, and the polynomial is a determinant of the matrix we have with negative t, with t subtracted from its diagonal entries. And again, the formula will be probably the easiest way of computing it. The product of diagonal entries will be t squared times 1 minus t. Then this 3 will come with plus sign, and the product is just 0, and this will come with plus sign, but again the product is 0. And so we have to start looking at negative products, 3 such, and this negative product is 0. This product is negative t, and it comes with negative sign, so contributes as just t, and the same for this product. So we have 2 such contributions, making the polynomial look like that. And we need to find the roots eventually, so we need to factorize the polynomial. We don't need to expand, we rather need to factorize. So t can be factored out, leaving us with t 1 minus t plus 2. And then here, to apply quadratic formula, we have to expand, and we'll have starting with lowest term 2, and we'll have t, and then we'll have negative t squared. So that quadratic again is straightforward to factorize. Its roots will be 2. If we substitute 2, we'll have 2 plus 2 minus 2 squared, which is 0. And the second root is negative 1. So if we have negative 1 and negative 1 again, we'll have negative 2, which cancels this free term out. So together with the 0 root, we have our 3 roots. the spectrum in terms of eigenvalues, which were originally after their set. The spectrum consists of 3 numbers, which means, because of the 3 by 3 size, that we will going to have just one up to scaling eigenvector for each. There will be no multiplicities. We have as many eigenvalues, different eigenvalues, as the size. So let's start computing eigenvectors, starting with eigenvalue -1. We have to solve linear system with a matrix. The original one with -1 subtracted from the diagonal. Another way, we have to add to the diagonal entries 1 everywhere. So that is the matrix. And then Gauss elimination is a tool. Eliminating the first column, we can do it by row subtraction. We'll get 0 here, we'll have 1, and we'll have 1 again, and then we're almost at the row echelon form. We just need to do one more subtraction to eliminate completely the last row. It's 1 here, and then row of zeros. And that is a row echelon form, and all we need to do now is to reduce it, so to create 0 above the second pivot, again by row subtraction. We can do it easily. Now we are done. We have 2 clean pivots, just sitting alone in their columns, pivotal columns, and then we have one last column corresponding to our free variable, which can be made whatever we like. So when we make it 1, this last free variable made 1, will make the second variable -1, the second coordinate will be -1, the first will be +1. So that up to scaling is a unique eigenvector with eigenvalue -1. Let's continue with the next eigenvalue 0. This time we don't need to alter our adjacency matrix at all. We just need to solve a homogeneous linear system, the homogeneous linear system with this matrix. And of course, matrix is degenerate because it just has 2 identical rows. So we can rearrange the rows, put the second first, and then immediately do the cancellation, just eliminating one of the identical rows. And that is a row echelon form, and then we reduce it by subtraction of the second row from the first. And again, the last variable is a free variable, and we can make it 1, and then the other 2, the first and the second, will be determined. The second is 0 no matter what. That's what its equation is saying. And the first is negative the last, so that will be up to scaling again a unique eigenvector with eigenvalue 0. The last eigenvalue we need to compute for is 2, and here we are subtracting 2 from the diagonal of our adjacency matrix, and that is the result. And we have to again make a reduced row echelon form to see the solution. So put in the second row first, and then subtracting it or adding it twice to row 2. We will have 0, we will have -1, and we'll have +2. And the last row, I know something is quite right. That is not going to work, but let's just check if everything goes correctly. So I'm subtracting, or rather adding twice this to that. That will create 0 here. And -2 plus 1 is -1. And 2 plus 1, yeah, 1 twice plus 0 is 2. Because I copied this incorrectly, that's why I'm having troubles. That is the correct form. I just didn't carry negative sign in the first transformation. So now we have again up to sign identical rows can be eliminated quickly. For example, row 3 plus row 2, transformation which makes last row identical 0, and then we can change the sign of the second to make it look better. The last transformation to turn this row echelon form into reduced one, just row addition. Now we have perfect assembly of pivots, and then we'll have -2, -2 in both of our pivotal equations. And as before, the last coordinate is 3, making it 1. We will have again, something is amiss. I was carrying it wrongly, so that is supposed to be 1 here, and that is still 1. And now when I add -2 to it, I will have -1. So that is up to scaling a unique eigenvector. And that's what already is going to be the start of our diagonalization answer. So A is going to be possible to write as a conjugate like that, with middle matrix D being diagonal, and this diagonal matrix is the matrix of eigenvalues, -1 first, 0 second to last. So that is the diagonal answer, and the G, the matrix built out of eigenvectors, is already here. It has the first eigenvector for -1, the second for 0, and the last for +2. All we need to do now is to find G inverse. All we need to do, so finding G inverse will give us this complete diagonalization, and G inverse we can find in at least 2 ways. Let's do it through extension method. So we do it by Gauss elimination of the matrix extended by the identity matrix. And can start by clearing the first column. Adding to row 2, row 1. And then we'll have -1, and we'll have 3 here, and then we'll have 1, 1, and 0. Also subtracting from the third will also make us 0 in the first column, and then we'll have 2 and 0, and then we'll have -1 and 0 and 1. And that is good start. So we created our first pivot. We can continue with -1 by multiplying it by 2 and then subtracting. But alternatively, we could already use this as a second pivot. It is twice 1, as it should be, but yeah, we could still kind of use it as a second pivot. Let me show what I mean. I will just put row 2 in the second place. And the row 3 goes down to the third position, and I will double it at the same time. So I will do several transformations at once. Instead of division, I will be scaling up so that my elimination goes smooth. And then I can eliminate by just row subtraction. So this time I'm just subtracting row 2 from row 3, or adding rather, because in row 3 it is negative 2, and I will have 0 immediately, and I'll have still 6 here, and then adding will give me 1 and 2 and 1. Continuing. Now we are in the row rational form, and we have to eliminate upwards. Here we have numbers not really proportional to 6 or 2 with integer coefficients, but we can scale up again the first row by 6. So in that, everything will be divisible by our pivots. And now we can eliminate easily. So first transformation, row 1 minus row 3. 6, negative 6, 0. And then subtracting, we'll have 5, negative 2, and negative 1. Effectively, the final transformation is to do elimination. In the second column, you can row addition, row 1 plus 3 copies of row 2. We'll have 6 and 0 and 0. And that is continued by, so adding 3 copies. Right, am I adding or subtracting? I am adding 3 copies. 3 copies of that, right, of negative 1, 0, 1. So 5 plus 3 copies of negative 1 will give me 2. Negative 2 stay put, and then negative 1 plus 3 copies of 1 will give me 2 again. So the final move is really an easy one. I'll just scale everything down or everything up, but just scale this by 3 up, and then I will have in the left side the identity matrix scale up by 6. Or I can just let me do that. So twice row, or rather 3 times row 2. So in this I will have just the identity matrix uniformly scaled by the same number. Scaling by 3 will raise this to negative 3 and 3. Then we'll have 1, 2, and 1 remaining in the last. And now to make the answer for G inverse, I just need to divide by 6, which incidentally is a determinant of our G matrix, if you wonder. And that is the answer. So this right-hand side divided by 6 is the inverse. We could check by doing some computations in the product. Say of G inverse on G by taking this with that, we'll have 2 negative and negative gives us positive 2 in here, and then 2 again, so 3 copies of 2 over 6 gives us 1. Taking this with that, we have 2 and negative 2 and 2 cancelling out, so looks promising, but indeed this is G inverse. Now we have all ingredients for the diagonalization, and the last step in computing the powers is to use this diagonalization. So we can now write the power as a conjugate of the power of the diagonal, which is so much easier to compute. So let's write this in matrix, complete matrix form. I'm putting the coefficient for the G inverse in front of the whole product. First comes G, then the nth power of D, which will be negative 1 to the nth power 0 and 2 to the nth power on the diagonal, and zeros everywhere else. And then the bulk of G inverse. So all we need to do now, let me put a divider between the previous computation and the current one. All we need to do now is to compute the product. And that will give us the answer for arbitrary entries of an arbitrary power of our adjacency matrix. The first, we multiply the first two. It will be negative 1 to the power n as a product of this row and that column. So here, column full of zeros will give us 0, and will be 0 here, and will be 0 here. And this by that will be just 2 to the n. And then this by that will be negative 1 to the power incremented by 1. This by that will be 2 to the next power. And this by that is again negative 1 to the power n. And this by that is 2 to the power n. And that is the product of the first two. And the third is this bulk of the G inverse. Continuing, we just need to multiply the two. So the first entry here is the product of this row and that column, and it comes as negative 1 to the power n times 2, and 0 kills negative 3, and then 2 to the n. Continuing with computing the first row of the answer, we have to multiply this with that, and it will be negative 1 shifted by 1 power because of negative sign absorbed into the power times 2. Plus these two together, again, it's the next power of 2. Finally, the entry here is the product of this line and that column, and it will be negative 1 to the power n twice, plus 2 to the n. Continue with the rest of the matrix. This by that will be negative 1 to the power n plus 1 twice, this 2, and these 2 will give us 2 to the n plus 1. This by that will be negative 1. Again, we can absorb the negative sign into the power, shifting it by 2 this time, and that again is the power of n shifted by 2. This by that will give us -1 n plus first power twice plus 2 to the power n plus 1. That by this is -1 to the power n twice plus 2 to the n. Numbers repeat. This by that is -1 to the power n plus 1 twice plus 2 to the power n plus 1, and this by that is -1 to the power n twice plus 2 to the power n. So there's a certain pattern in the matrix which we can uncover by introducing a new quantity. Let's call an -1 to the power n twice plus 2 to the n over 6. So just absorbing this prefactor. And then we have an here, we have an here in the corners. In these 4 positions, we have the next in the sequence formed by an. And in the middle, we have next after. And that is a shape of the specifics of the matrix, specifics of the graph even manifested, which again suggests that the computation is done right. So that is, by the way, we can simplify that, factoring 2 out, maybe changing the order, 2 to the n minus 1 after cancelling 2. So we have 3 in the denominator, and then plus, or rather minus, negative sign to the power n minus 1 to make the powers aligned. And that is an integer that has to be a natural number, non-negative integer, because we are raising to the nth power a matrix which has non-negative integers as entries. We are counting path in the graph. And it is because that numerator is always divisible by 3. Simply because 2 and -1 have the same remainder, modulo 3, the difference will have remainder 0, hence divisible by 3. So these numbers are always integers, natural numbers. And that's what the answer is. So I'll just copy it in here. And this is much quicker than, say, computing matrix products. So for example, we want to know how many paths in the graph are of length 11, say, starting at here and ending in this vertex, at this vertex. So that will be computed by A11, and by the formula, A11 is 2 to the 10th power minus -1 to the 10th power is just 1 over 3. So 2 to the 10th power is 1024 without 1 divided by 3. That is 1023 divided by 3. And we could break 1023 into 2 bits, like 3 nines, and then 24, each of them manifestly divisible by 3 in an easy way. So the answer is 3, 4, 1. That is, of course, was much quicker than counting all the paths of length 11. And of course, we have that many of them. So one of them, for example, would be going to the left, to the right rather, so we have to do it, there's no other way. And then doing 9 loops and then going to the right again. But there will be 340 more. That is it for the application of diagonalization of adjacency matrices. See you later.